In the quantum world, tiny particles never travel along just one path, but instead move along all possible paths at the same time. Doesn't that sound a bit unbelievable? I used to think the same way. I believed that any object in space could only have one fixed trajectory, at most a straight line. But later, I realized that this idea was completely wrong. Humanity's earliest understanding of the world was based on determinism. That meant believing motion was linear, with direct cause and effect relationships. Newtonian mechanics tells us that if we know an object's current position and velocity, we can precisely predict its future state. People were immersed in the comfort of this determinism, as if the universe were a giant clock. Once the spring was wound, it would run endlessly along a single, predetermined track. However, the emergence of quantum mechanics completely shattered this intuition. Let's start with an everyday example. Imagine you're on a beach, and you see someone drowning. If you run straight into the water, you may enter the sea quickly, but you'll have to swim a longer distance. If instead you run a few extra steps along the sand, and then enter the water at an angle, you might actually reach them faster. Light behaves in the same way. It automatically takes the fastest path. This is the famous principle of least time, also known as Fermat's principle. But here's the problem. Light has no consciousness. So how does it know which path is the fastest? Classical physics can only tell us, in broad terms, that light refracts, but it cannot explain the mechanism behind it. It wasn't until deeper study of quantum mechanics that people realized something surprising. Light never actually makes a choice at all. It simply travels every possible path, and the path we observe as the fastest is merely the result of interference among countless paths. This shift in thinking began with Planck's discovery. In 1900, while studying blackbody radiation, he encountered a terrifying paradox. If energy were continuous, the theory predicted an ultraviolet catastrophe, where energy at short wavelengths would diverge to infinity. But experiments showed that this did not happen. So he proposed a shocking hypothesis. Energy can only be exchanged in discrete, discontinuous quanta. Each unit of energy is not arbitrary, but divided into tiny chunks. The size of these energy chunks increases as frequency increases. The proportionality constant behind this relationship is the famous Planck constant. For the first time, people realized that continuity in nature was actually an illusion. In 1905, building on Planck's ideas, Einstein proposed the light quantum hypothesis. He argued that light is not a continuous wave, but is composed of individual photons. This idea explained the photoelectric effect, and earned him the Nobel Prize. As quantum theory developed, Bohr proposed the quantized model of the hydrogen atom, arguing that electrons could only exist in specific orbits, otherwise atoms would be unstable. De Broglie took this further, suggesting that not only photons have wave-like properties, but matter does as well. An electron is not a tiny particle, but a kind of wave. It must form standing waves in its orbit in order to remain stable. This gave birth to the concept of matter waves. Electrons are both particles and waves. This wave-particle duality laid the theoretical foundation of quantum mechanics. In 1925, Heisenberg proposed matrix mechanics. The following year, SCHRDINGE introduced wave mechanics. At first, they looked like completely different formulations, but later, people realized they were describing the same reality. SCHRDINGE wrote the equation that changed the world. He used the wave function to describe the evolution of particles. But what exactly is a wave function? Is it a real physical entity, or merely a computational tool? This debate remains unresolved to this day. In 1927, Heisenberg presented an even more shocking conclusion. A particle's position and momentum cannot be precisely known at the same time. This isn't because experiments aren't good enough. It's because nature itself does not allow it. In other words, at its deepest level, our world cannot be fully predicted. This made the deterministic, clockwork universe collapse at its very foundation. To mock this apparent absurdity, SCHRDINGE proposed the famous SCHRDINGERS cat thought experiment. A cat's life or death is linked to a quantum event. Before observation, the cat is both alive and dead at the same time. From a macroscopic perspective, this seems obviously absurd. Yet this is precisely the essence of quantum superposition. Dirac went even further. He unified quantum mechanics with relativity, wrote the Dirac equation, and predicted the existence of antimatter. Even more astonishing, experiments eventually confirmed it, as if theory truly had the power to pierce reality itself. Despite all this, Einstein could never accept the indeterminacy of quantum mechanics. Together with Podolsky and Rosen, he proposed the EPR paradox, arguing that quantum mechanics must be incomplete. and that some form of hidden variables must exist behind it. Otherwise, the ghostly action at a distance, revealed by quantum entanglement, would be far too bizarre to accept. But in the 1960s, John Bell introduced Bell's inequality and tested it experimentally. The results left people speechless. Quantum mechanics was correct. Local hidden variables cannot explain quantum entanglement. In other words, the universe truly contains a form of non-determinism that goes beyond common sense. Building on this, Feynman proposed an even more radical idea. When a particle moves from point A to point B, it doesn't travel along a single trajectory. It travels along all possible trajectories. Every path contributes to the final result. Some paths cancel each other out. Others reinforce each other. What we perceive as reality is actually the superposition and interference of all possibilities. This sounds hard to believe, but it means that the certainty we experience in daily life may actually be an illusion. In the 1950s, Hugh Everett proposed the famous many worlds interpretation. In his view, quantum superposition never collapses. It exists simultaneously as countless parallel universes. Every measurement is essentially a splitting of the universe. In one universe, the cat is alive. In another universe, the cat is dead. This forces us to rethink whether what we call destiny might be like the path of an electron, unfolding simultaneously across countless parallel worlds. The many worlds interpretation tells us that every possibility may indeed occur. We simply experience only one of them. When you look back at how light chooses its path, doesn't it suddenly feel more profound? Light has no intelligence, yet it seems smarter than we are. It doesn't make choices. It allows all possibilities to happen, and then reveals the optimal result through interference. What about our lives? Perhaps it's the same. We think we are making choices, but maybe we are simultaneously traveling along countless unseen paths, ultimately experiencing just one. Determinism once gave us a sense of security, but quantum mechanics reminds us that uncertainty is the true backdrop of the universe, and within this uncertainty, free will may not be an illusion at all, but a space hidden deep within quantum reality. You see, science may appear to be explaining nature, but it is also explaining us, who we are, how we exist, and what our choices truly mean. Quantum mechanics has not only changed physics, it has also changed philosophy, and transformed our understanding of freedom, destiny, and the universe itself.